Let's imagine you're trying to master a sport like tennis. One day, you play on a clay court, another on grass, sometimes with a heavy racket, sometimes with a light one. To truly become a remarkable player, you'd want to adapt quickly to any new situation, regardless of the surface, racket, or even weather. Now, think of artificial intelligence. We want machines not just to learn one skill in one specific place, but to jump into new environments, perhaps entirely different from anything they've encountered before, and still perform strongly, almost instantly. Today, I'm going to explain a powerful approach that's trying to do for AI what world-class adaptability does for athletes: meta-learning with task-adaptive regularization, aimed at rapid domain generalization in non-stationary environments. So, what exactly does all that mean? Meta-learning, sometimes called learning to learn, is a branch of machine learning where algorithms are trained not just to solve one task, but to rapidly pick up new tasks. The goal is to mimic human-like flexibility. Just as we can generalize from old experiences to tackle new challenges, meta-learning tries to empower AI with this skill. But in the real world, environments are non-stationary, they change constantly. Imagine a self-driving car that suddenly finds itself in a snowstorm after operating only in sunny California, or a medical diagnostic AI confronted with new, never-before-seen diseases erupting in a different country. How can an AI generalize quickly to these new, out-of-domain scenarios, ones that are different from anything it is trained on before? That's the domain generalization problem. Enter task-adaptive regularization, a smart trick that helps machine learning models keep from getting too attached to their training data, so they don't overfit to the familiar and can instead perform adaptively in the unfamiliar. Let's break down how this works. Regularization in machine learning is a little like giving rules to a student doing homework. Don't just memorize the answer, understand the method. Standard regularization methods might say, don't let any one part of your model be too influential, to avoid overfitting. But with task-adaptive regularization, this regularization changes, or adapts, based on the specific task the model is facing. It's like a tennis coach saying, if you notice you're on clay today, use longer slides and softer serves. Meta-learning algorithms can explore many small tasks during training, such as recognizing cats and dogs with different lighting, backgrounds, or camera types. For each mini-task, the model learns how to regularize itself to prevent overspecialization. Over time, the AI essentially learns how much to flex its understanding, so when it faces something brand new, a chord it's never played on, so to speak, it can recalibrate almost instantly, without forgetting what it learned before. To help visualize, picture a hiker who's not just memorizing one trail map, but learning how to read any map, notice weather patterns, and pack the right gear for surprise conditions. When thrown into a strange forest, the hiker might not know the exact paths, but thanks to meta-learning with task-adaptive regularization, they quickly piece together clues and adapt to surprises, instead of stumbling or freezing. This is the kind of agility AI researchers are aiming for. Let's move to a few concrete examples of where this approach might shine. One scenario is in robotic assistance for disaster zones. Imagine a robot trained in a pristine laboratory, suddenly deployed to a muddy, smoke-filled rescue situation after an earthquake. Because environments shift unpredictably, traditional training wouldn't prepare the robot for this. But with meta-learning and adaptive regularization, the robot can adjust its navigation and perception skills on the fly, handling new chaos and debris with surprising robustness. Another example is in healthcare. Suppose an AI imaging tool is trained mainly with data from urban hospitals, but a rare, unfamiliar disease appears in a rural community with different imaging machinery. Meta-learning with task-adaptive regularization means the AI won't throw up its hands. Instead, it adapts its diagnostic reasoning to the new, never-before-seen data, helping medical teams even when information is sparse or unusual. A third domain is virtual personal assistants exposed to different dialects, slang, or completely new topics. Rather than being baffled or making embarrassing blunders, such assistants could quickly recalibrate their language understanding to serve users better, regardless of who speaks or what's discussed. So why is this so important, and what's the big impact? As our world changes rapidly, think climate, healthcare, global commerce, we can't anticipate every twist and turn. AI systems need to keep up, not collapse, as circumstances shift. Meta-learning with task-adaptive regularization means we don't have to exhaustively retrain models every time a new challenge appears. Instead, our models can be agile, flexible teammates learning from past experience how to adjust themselves, like seasoned professionals dropped into new arenas. This saves time, resources, and opens the door to deploying AI in settings where data or supervision is scarce. Now, you might be wondering, is this technology going to make human experts obsolete? Not at all. Just like the best athletes benefit from great coaches, these meta-learning models extend our capabilities. They become better partners for people, not replacements. Another question might be, is this the kind of technology inside systems like ChatGPT? While major chatbots and language models use some related meta-learning techniques, task-adaptive regularization for domain generalization is still more of a cutting-edge research topic but is rapidly influencing how next-generation AI is designed, especially for robust, real-world adaptability. To wrap up, consider how, in an unpredictable world,